Hi everyone, in this video we are going to compare Google's BigQuery to AWS Redshift. Now both BigQuery and Redshift are solutions geared towards handling very large volumes of data specifically for analytical workloads. However, comparing BigQuery to Redshift isn't exactly comparing apples to apples. If we were to do a true apples to apples comparison, we need to compare BigQuery to a suite of AWS offerings which includes AWS Redshift, Redshift Spectrum, and AWS Athena. And only then is it really an apples to apples comparison. So that's what we'll do first. We'll try and understand what these technologies are from AWS, and then we'll take a detour and look at the underlying architecture. So specifically, we'll look at the architecture for BigQuery and Redshift. Again, I've done a separate video, and there's a link you'll find in the description to that video where there's an elaborate video on just AWS Athena. So I'm not covering that content again in this video. Would encourage you to take a look at that after you've seen this video. So we'll look at the architectures and compare and contrast the architectures, and then finally we'll be able to compare BigQuery to Redshift. Again, the comparisons really geared towards decision makers. So if you were trying to compare the use of BigQuery versus Redshift for your project or for your organization, hopefully you'll find this information helpful. So with that said, and the goal and how I've structured the video, let's dive in and look at the AWS options. So let's move on to the architecture of AWS Redshift. We'll look at it at a 10,000 feet overview, and then we'll go a bit more closer and look at what it looks like under the hood. So if you're familiar with MPP architectures or massively parallel processing system architectures, like if you have looked at the architecture for, again, if you have looked at, say, Presto's architecture, or if you have looked at architecture of Apache Impala, then a lot of this will be familiar. So you have the construct of a master node and a slave node, or also referred to as a leader and compute node. And the outside world basically only talks to the leader node, and the leader node coordinates with the compute node. So essentially the outside world does not know about the existence or cannot communicate directly to the compute nodes. Now, given that I mentioned already that AWS Redshift is based off of Postgres, that essentially means to the outside world, be it a BI reporting tool, or if you have written code, say through Python or Java, for example, all that code basically thinks that they're talking to another to another Postgres instance. Again, there are some subtleties, and again, Redshift, there are specific drivers that you have for Redshift, but to the outside world, they basically think that they're talking to a Postgres backend, which is actually quite amazing when you think about it from an adoption standpoint and support for various tools. So there's again a JDBC driver and a ODBC driver. Now, the unit of parallelism specific to Redshift is what's referred to as a slice. So essentially, when you provision your infrastructure, the resources like RAM and storage, etc., are basically split into a unit called a slice. And a slice is essentially how a query is basically parallelized. And when you have the leader node send a piece of work to compute nodes, it kind of splits it across based on the number of slices. So again, the number of slices are determined by the underlying compute node infrastructure that you specified when you're provisioning the node. So having looked at it from a high level, let's look at it in a bit more detail, kind of look at what that flow looks like. So again, say you have a BI reporting tool or a client application that sent a SQL query. It's received by the leader node, which basically parses that query. And when it passes the query, it does some intelligent optimization. So for example, it knows if it's received that query in the past. If so, it uses a cached copy of the code that was generated by the query. If not, if this is the first time that it's received that query, it tries to basically break down that query and creates a code, a compiled code of that. So again, it's very similar to how a traditional database would do that, but in this particular instance, it knows that, or it tries to break down that query with the understanding of co-location of that data. So again, co-location is a familiar territory if you're coming from Hadoop and Hive or many of the MPP engines. Is the idea that you don't want to bring data to compute, you want to run the compute where the data is. So it knows in advance that this segment of the data resides in either compute node 1 or compute node B or C. So it tries to route the compute on to the node which is actually hosting the data. So it does that quite intelligently, and it breaks it down and segments it. And then it uses the Redshift workload manager. So now the workload manager is an interesting piece of technology there, and it's something that you'll find that you need to configure and tune based on your workloads. So essentially, you don't want all the queries to say have the same priority. You might schedule it so that some ETL job, say for example, an end of day batch job, has a lower priority than batch jobs that are interactive in nature or batch jobs that are meant for reporting. So for example, you have reports that are viewed by the finance team, or say for example the executive leadership team. Dashboards will have a higher priority that you can assign to those queues than something like an ETL type or a daily processing kind of like a workload queue. So again, all that is configurable through the workload manager. So when it receives a request based on the account that's using that was used to send that query, it decides what the priority of that workload is and schedules the job accordingly. And then the requests are passed downstream to the individual compute nodes. The compute nodes process the data locally. Again, you have the idea of co-location again coming in. So it processes the data and it parallelizes that processing using slices that we spoke about earlier. And once it processes the data locally, it sends that data back upstream, and it uses the leader node again is responsible for kind of like joining up the data that it's received from all of these compute nodes and sending the query results back to the client application. Again, there's a lot of administrative functions that it does, so I'm going to skip that in the architecture again to keep things brief. But again, there's quite a lot more that goes on under the hood. But that's AWS architecture in a nutshell. Again, the architecture itself haven't described AWS Redshift Spectrum, but essentially when a query comes to Redshift Spectrum, when a query comes into Redshift, the query planner, based on the query, it knows that some of the data, if it's in sitting in AWS S3, it will send requests out into AWS Redshift. So that's handled kind of transparently for you, so you don't have to do anything explicitly to handle Redshift Spectrum queries. Finally, the last thing to mention on the architecture here is particularly about things like caching. If AWS Redshift receives a query and it knows that it's already processed that and the data hasn't changed, it'll serve the data from cache, so that alleviates the system from having to perform those computations again. As of this moment of when I'm recording the video, the caching is specific to AWS Redshift and not Redshift Spectrum, but if I'm not mistaken, things are going to change, and even Redshift Spectrum caching will be supported in the future. So that's it for AWS Redshift architecture. Moving on to Google BigQuery. So a lot of what we know about BigQuery is based off of the paper that Google had produced about a decade ago. Wow, can you imagine a decade ago? Google was that advanced a decade ago, and a lot of the inspirations for SQL on Hadoop and SQL-like technologies, distributed SQL technology, was heavily inspired by the paper that Google had produced on Dremel. So a lot of what BigQuery does is based off of the same underlying architecture, and it's very much a black box. But again, we do know some details about how BigQuery operates. So at a high level, you have a serverless solution that's managed fully by Google. So there's a compute element and a storage element, and connected by a very high performant petabit network. So historically, you had again Dremel, or rather BigQuery is basically an externalization of the internal solution that Google had. Again, they had a compute cluster and a high performance storage cluster. The internals of the Dremel paper indicated that the storage was basically based off of Google's distributed file system, GFS, which was later Colossus, and you had a high performance network, Jupyter network. So that's how Dremel worked, and BigQuery uses the same underlying principles. Also keeping in mind that you had different ways that you could ingest data into the environment. So the bulk loading was done at a no cost. However, if you were doing a streaming ingest, there was a cost, separate cost that you had to pay. If I'm not mistaken, it was a pay per data volume. Again, you'll find that even in Redshift, you have similar options to do bulk as well as streaming ingest. The streaming ingest you eventually pay for in even in AWS. So, for example, if you're using something like AWS Kinesis to send the data into AWS Redshift, you still pay for utilizing the Kinesis data services. And then finally, from an interface standpoint, note that you are not working through a JDBC or an ODBC. You're basically interfacing via a REST endpoint. You have client libraries in all the major programming languages, which behind the scene is using the REST API to interface with BigQuery. BigQuery has its own design elements, so which are unique or to BigQuery. But again, the good news is that it's all based off of SQL 2011 compliance standards. So even though BigQuery uses, oops, let's get that out of the way. Even though BigQuery uses um, constructs such as records and arrays, data structures. Behind the scene, it's all compliant with SQL 2011. So if we peel it a little further, what does what does Google BigQuery look like under the hood? To your client application, regardless of whether it's a custom-grown, homegrown application, or if you're using a BI, third-party BI tool as a client application, all your requests get sent to a regional router, and your regional router, this is all handled transparently behind the scene within BigQuery, sends it to a job server. Now the job server needs to know, given that you have a massive scalable system from a compute environment, the job system again tries to figure out which environment it needs to send the job to. So a lot of the metadata for BigQuery is stored in Google's own Spanner. So again, Spanner is a large-scale database, which again is an independent service which we can directly use. But it's interesting to note that Spanner is used to manage a lot of the table metadata, and once it knows which data lies in which place, that's when it can orchestrate the job much more efficiently. So note that Google in the BigQuery does not use, though it uses a columnar storage, specifically called as capacitor and capacitor files, it does not utilize columnar storage internally, like, say, for example, Parquet or ORC. It uses their own proprietary format called capacitor. So again, a capacitor lies in the distributed storage, and it uses a worker or n-tiered worker nodes to aggregate and perform shuffles and aggregates that data finally into the master. So unlike Redshift architecture, the master node does less of the heavy lifting, and more of the aggregation and joining up of the data is performed by several of these workers, and it does perform shuffles a lot more intelligently at intermediate levels. So that's Google's BigQuery architecture. So now we understand how the architectures of these two systems work. Let's move on to the final section and let's actually compare BigQuery versus AWS Redshift and Athena, again from the standpoint or the viewpoint of a decision maker. Now, comparing technologies objectively is a real hard problem because there's always one's personal experience with it, as well as any personal bias in terms of technology preferences. However, I'll try to keep it as objective as I can. Now, for purposes of what I'm explaining, anytime I'm referring to AWS Redshift, I'm referring to it as a collection of AWS Redshift, Redshift Spectrum, as well as Athena. So don't want to keep elaborating all those terms all the time. So Redshift, I'm using it as a collective to represent all those technologies. Now, in most cases, these would be common objectives that one would use. Again, I would encourage you to do something like a proof of concept for your own projects and derive your own objectives. Now, to get things started, I'd say if we look at technologies, and my personal opinion would be that regardless of what the underlying technologies help support you, the number one parameter I would evaluate it is based on the ability to execute and deliver success for your projects. And a key component of that would be the simplicity of the solution, regardless of the technology marvel under it. How simple is the service or the solution that's exposed to your project, and how quickly can your projects deliver the solutions and make decisions and move ahead and deliver the project to success. With that parameter and with that objective, there is a clear winner, and that's Google's BigQuery. So unlike the Redshift option, again, Google's BigQuery being a serverless solution makes delivering that, deploying the solution, and leveraging the services very, very straightforward. There aren't that many options when it comes to Google's BigQuery, and having options is both a blessing and a curse. But specifically in terms of simplicity, realistically, it doesn't take you more than 5 minutes to get started with BigQuery. In terms of decision making for your projects, what I've commonly seen in scenarios which involve Redshift is Redshift projects tend to be structured like your traditional Teradata style projects where you have a centralized team, a shared service team that manages a big large cluster, and onboarding for projects and new entities and data sources tends to be like very much like a bottleneck depending on how your team has been structured. Not so for BigQuery because individual projects can operate independently. You have less of a shared dependencies from a project structure, but also given the fact that it is a serverless solution implies that our teams can get started really quickly. There's less of provisioning and system management and oversight required. So hands down, this is a clear win for Google's BigQuery. Performance is a very subjective attribute, and there's plenty of white papers and published material outlining the performance of various technologies, including Google's BigQuery and AWS Redshift. Again, would encourage you to do your own performance benchmark. But historically, what I've seen, having hands-on experience on both Redshift and with BigQuery, is that again we have walked through some of the underlying architectures, and hopefully you'll appreciate that each of these technologies brings something similar to the table as well as some unique aspects. However, given you have a lot more ability to tune the performance and the query of Redshift, it's less of a black box and allows you to tune it in a lot more granular details. Here, I would grant that AWS Redshift is more performant. Now, again, it would require for you to get the maximum out of Redshift to optimize your data model to how Redshift stores its data, have a clear understanding of how it parallelizes your queries for execution, as well as manage your overall data management and workflow management. So it's not a walk in the park to get every inch of performance out of Redshift, but again, if you have a team that's committed to delivering high quality queries out of Redshift, then definitely you will find that performance in Redshift is significantly better. Though here I must distinguish between Redshift, Redshift Spectrum, and with AWS Athena. Redshift, the managed service instances will give you the highest performance, and you'll find that Google's BigQuery kind of like sits somewhere close to Redshift managed service in terms of performance, and Google's BigQuery, in my personal experience, has been better performant than AWS Athena. But overall, I would say Redshift tends to perform much better than BigQuery. Time will tell. Let me know in the comments below what your experience has been benchmarking the two. Finally, when it comes to things like cost, again, cost is also nebulous in terms of how you can evaluate it. But generally, these are some guidelines to measure cost. While Google's is a serverless solution, so you pay per query, historically when BigQuery was released, you only had a model where you paid per query, in which case it's a pay-as-you-go model, and your monthly cost could kind of fluctuate significantly based on the number of queries. While you pay separately for storage, most of the time the cost was in terms of the number of queries and the volume of data that a single query had to pass through. More recently, Google's also released a fixed cost per month, so it's very similar to how you would cost it for Redshift. So again, in case of Redshift, you have a fixed cost for your cluster, your managed service, and you have a variable cost for running Redshift Spectrum queries and Athena queries. Again, they have similarities, but overall the way you can evaluate it would be based on how much of idle time you have. So if you have a lot of idle time in your infrastructure, then obviously a serverless model makes more sense. Whereas if you had a steady workload, like a predictable workload, and your cluster was kind of in a steady state pretty much throughout the day, then obviously something like Redshift would make more sense. So here there's no clear winner here. However, I would argue that in most of the projects and clients that I've come across, the Google's BigQuery model would be more cost effective. So again, it depends on your workload. There are several parameters. Now, the key thing to keep in mind is, while not often quoted, is the idea of data caching. So if your data is cached, and both Redshift, the managed service, and Google's BigQuery does do caching natively, the idea is that if you had data that was cached and being served from a cache, so there's less overhead in terms of the underlying infrastructure. So if in case of Google's BigQuery, if it finds that data set can be served from cache, you don't really pay for that. You don't have to pay for additional compute and query if the data is already available in a cache. So typically think of it like a BI dashboard. If everyone's coming and looking at that data for a 24-hour window, it's essentially running, if it is running the same query and the underlying data hasn't changed, then there's really a lot of cost savings when you're looking at data caching. Google's BigQuery, in addition to a native data caching, also gives a relatively new feature called a BI engine. Now, the BI engine is clearly targeted towards data caching in support of BI and dashboard kind of like applications. It's relatively new, but very promising technology. Unfortunately, it's very much a black box without a lot of details into the technical know-how or the technical specifications. But again, it alleviates from in having to worry about running large number of queries, hammering away at BigQuery, and resulting in a very large bill at the end of the month. AWS Redshift, again, as I mentioned, natively gives you the ability to cache data. Caching is kind of in flight from a development for Redshift Spectrum, as I understand. And also when it comes to Athena, Athena under the hood does cache the result. Basically, the results of Athena are stored in an S3 bucket, and client applications basically query the data from the S3 bucket. So essentially, it does give you caching natively, but that's not how it is directly interfaced with using client libraries. So again, it's dependent on your client libraries or third-party tools to actually benefit from caching. So again, caching saves you both money and can result in much more performant and more faster query responses. So in summary, would evaluate how well your cluster is going to perform under different load styles and how much of idle time it has, and you can take a stab at how much of cost or savings of cost you have one from the other. The last bit is around the ecosystem, because so far we've been talking about how quickly you can develop the solution and how agile your projects can be and performance. But a key factor in delivering a solution is looking at it from an overall ecosystem in terms of third-party solutions, open source solutions that allow you to both connect and analyze the data. Here, there's a clear winner in my opinion, and that's AWS Redshift. Redshift, as I've described before in this video, is based off of Postgres. So I'm talking specifically about Redshift, the engine, not Athena, but Redshift itself. Now, Redshift, given that it's based off of Postgres, basically implies that the vast majority of all the tools that you have used, both development tools, if you have used any GUI tools for your development that connect to Postgres, it should work with AWS Redshift. So again, from a tooling standpoint and from the vendors that have BI reporting and analytical applications, they readily support Redshift. Now, Google's BigQuery interfaces with REST APIs and with with client libraries in all the major supported programming languages, but still, it's still not as widespread as AWS Redshift. And finally, with regard to the other data management capabilities that you have within the cloud, AWS is offering, while there are many, many options to choose from, collectively represent a much more mature and a much more thought through design. So for example, if you look at AWS Redshifts capabilities such as Glue and things like Glue Catalog, it's much more interconnected with all the other data services, including Redshift, Redshift Spectrum, and Athena. So from the breadth in terms of what you have within the data management within the respective clouds, AWS is offering, in my opinion, is better than Google's BigQuery. Of course, all of these points I mentioned are at this point in time, and in the future, both companies continue to innovate and expand their offerings. Overall, these are fantastic technologies, and you can't go wrong with anyone. And by and large, the decision to go with either Google's BigQuery or with Redshift is very specific to your organization. And if your organization's already invested heavily in one cloud vendor, and that makes decision a default. But overall, I hope this conversation's been helpful in terms of understanding the options that you have and then looking at the underlying architectures, and finally, hopefully an objective comparison to help you in your decision making. That's it for this video. Hope this video has been helpful, and if you can help the community, it'll be fantastic if you're in the comments below you can mention what were your decision points that allowed you to or enabled you to make that decision of one vendor or the other, and finally which vendor you preferred. Thanks for watching, everybody. Look forward to your comments. Bye.